Welcome back, everyone. I hope you are doing great despite your tight schedules and your load for day-to-day job. Today, we are going to practice some tests that are applied to the non-normal distributed data. The tests we are focusing include Wilcoxon tests, which are one sample and two sample Wilcoxon tests, and the Mann-Whitney U test. All right, so let's see together, and we are using our R Studio as normal. So please ready. Okay, so I have a pre-written code for you. I just go line by line in order to explain to you. And this is our main topic, is doing comparison using quantitative data that are not normal distributed. And the tests that we are going to use today are Wilcoxon and Mann-Whitney. These tests are indicated again. These tests are used, okay, when the data is not normally distributed, okay? And the data set that we are going to use today is from the library Mars, all right? And the name is car93, all right? So first of all, we need to load the data in order to, load the library so that we can load the data next. Okay, so the library is now loaded. And second, we load the data, all right? And in order to know what the data is, how many variables, what are the description, you can type a question mark or you can ask the R program to tell you, all right? So you can type question marks and then the name of the data, and then you will see the description. Okay, so on the lower right here, you can see the description of the data cars 93, which is the data from 93 car on sale in the US in 1993, which is long ago. And as we discussed a long time ago, that in order for us to call the data back and to be easy for us to remember, we need to rename our data into a short form. In this case, I use DS to name the data car93. Okay, right? So now the data is already loaded. So DF, if you want to view the DF, you can click on the DF on the working environment on the upper right, and you will see after clicking. So these are the data set that we have, and many variables starting from the first one, manufacturers, and second, model, the third, types of vehicle, and the fourth is the price and extra until the last variable is make. So the last variable is on the column number 27. All right. So you can just close the dataset and then you can come back. Okay. So like I indicate in the beginning, that today we focus on the non-parametric tests, which are Wilcoxons and Mann-Whitney. In order to do so, we need to know what are the variables that are quantitative so that we can conduct the test. To see that, first we need to see the names of the variables, okay? And you can also see the several lines of the data so that you know whether they are quantitative, normal, or ordinal, okay? So here, you can see, so the data that have number, in particular, the number that we can calculate, we can do math, they are the quantitative variable, and we can use in order to do the comparative analysis using our test, okay? You see the first 6 lines of the data DF, okay? And next, we need to check how many variables, how many quantitative variables of the DF have normal distribution and how many are not normally distributed by using this code, okay? So we use the supply and then the list, and the second argument is the test, which means Shapiro test, okay? So we just execute. So after checking, you can see that after checking, right? So we have many variables. So price, min price, max price, and price, they are not normally distributed. MPG city, they are not normally distributed, okay? So these are the variables that we can apply for the non-parametric tests that we are focusing, which are Wilcoxon and Mann-Whitney. For a summary, which is easy for us to follow later, so I make a note here. So non-normal distributed variables include the price variables, the MPG mile per gasoline in the city and highway, and engine size, horsepower, passengers per car, and the width of the car. Okay. After knowing the data of variables that have no normal distribution, we can now do the practice. Okay, so the first one is called one sample Wilcoxon. And our variables that we are going to practice is name passengers. And during our class, we propose a hypothetical value of 5, all right? So one sample test we use in order to compare the data of our sample to a hypothetical value. For a parametric test, we compare the means of our sample to a mean of the population or any hypothesized value. For a non-parametric test, we compare our sample to a hypothetical value, okay? So we can compare the central point, the central value, okay, of our data, all right? For the null hypothesis and the alternative hypothesis is that, so for the null hypothesis, we can say the number of passengers per car is not significantly different from the hypothetical value of 5. Or in other words, okay, the number of passengers per car equal to 5. And the opposite is the alternative hypothesis, meaning that the number of passengers per car is significantly different from the hypothetical value of 5. Okay, so the code that we are going to use, the function is Wilcox test, okay, Wilcox.test. And then inside the bracket, we need to know the variable that we are going to compare, I mean the data of the variable. So the variable we are comparing is passenger. And the value that we are going to compare against is mu equal 5. After that, you can make a, you can run the code, okay, here. So this is a, okay, Wilcoxon sign rank test, okay. It is a Wilcoxon sign rank test, all right. So the p-value is here, okay, 0.315, which is bigger than 0.05. If it is like that, then we accept the null hypothesis that there is no significant difference between the central value of our variable, the passengers per car, okay, from the hypothetical value of 5. Okay, so this is the meaning. Okay, we accept the null hypothesis, meaning that, okay, the number of passengers, the data of passenger per car is not significantly different from the value 5 we hypothesized earlier. Okay, now we can practice on another variable, engine size. Okay, so I'm not going to show you the nulls and alternative hypothesis again. I just make a code in order to run quickly. You can practice formulating the null and alternative hypothesis by yourself. All right. So in order to get a sense of the distribution of data, which is easy for us to make a hypothesized value, we need to do a summary of the data. Okay, we can run the code with, okay, summary, okay, summary, and then the data of the variable that we are going to use, okay, that we can execute. All right, so in the console, we can see that the minimum and the maximums of the data. Okay, you can make a hypothesis against the some value within this range, or you can make a hypothetical value which you prefer. Okay, in this case, okay, we use a 4, or we can say 5, but here just use 4. All right. Okay, now I use the same. Okay, our code is Wilcox.test, and inside the bracket, which is x, the variables that we are going to compare with the hypothetical value 4. Right? You can run the code, and then you can get the result here. Okay, Wilcoxon rank test. Okay, you can say mu. Okay, so here it is the mu's equal 4. All right. Okay, you can run. So the p-value is significant difference. All right. So it's a significant difference from this one. Okay. So in order to get that, you say there is a significant difference. So the p-value equal, you can copy here. All right. Okay. Here. All right. So we can say that there is a significant difference. All right. There is a significant difference between the central value of our data engine size to the hypothetical value of 4. There is a significant difference. You can also practice on another examples, which is max price, again, a value mu of 50, all right? So in order to get a sense of the data distribution, you can use the summary, okay? Can use summary. So the minimum is 7.9 and the maximum is 80. So based on our discussion and our suggestion in the class, we use the mu equal 50 for our test. All right, so you can use the Wilcox dot test, and then the x that you want to practice on, it means the variable max price against the hypothetical value of 50. Okay, and run the code. And now you can see the p-value is very, very, very small. Then we can accept the alternative hypothesis, okay? Meaning that there is a significant difference between the center values of the variable max price to the hypothetical value 50, okay? All right. So let's move to the two-sample Wilcoxon, which means paired sample. And as we discuss and we talk, we have a discussion in our class. See, we don't really have the data that have the exact pair sample or repeated sample in order for us to do the Wilcoxon paired sample. So let's create, okay, the variable year, okay, year to the 1990 and 2020. So to assume that there is a pair sample, one group are recorded in 1990 and another group in 2020. Okay, now we can append the variable year to the df by doing this code. Okay, df $year, which means we append the variable year to the df by concatenating, all right, the nominal data 1990 to a 46 with the nominal data of variable year 2020 to 47. So that 47 plus 46 equal 93 of our sample in the DF. All right, so we can run. And as we are going to do the pair sample, so we need 46 and 46. So the last sample must be omitted. Then we can subset a new data that have only 92 sample. Okay, so here is the code that we can do subsetting. We subset a new data from the old data df, and for the sample from number 1 to 92, and we take all the data of the variable. Okay, so doing this is to make sure that the sample size of the group collected in 1990 is equal to the sample group collected in 2020, meaning that each of the group has 46 samples each. Okay. Okay, so the variables that we are going to practice the pair sample Wilcoxon is horsepower. Okay, so make sure it is pair sample. Okay, and then make sure that you have to put the argument paired inside our code to T. It means they are paired. So paired here, they want to know whether the data we are comparing are paired or not. Okay, if it is paired, we say true. Okay, so our data set is paired. Okay, here we assume it is paired. Okay, one group collected in 1990 and another one collected in 2020. All right, pair sample, repeated measure. The number of sample must be equal. If two pair, so the first and the second sample must be the same. If 46 is 46. And afterward, you can run. Okay, I believe it's working now. All right. Okay, so the data here, the p-value is 0.76, which is bigger than 0.05, and therefore have to reject the alternative hypothesis, accepting H0. Okay, meaning that there is no significant difference between the horsepower data in the two periods. Okay, mean 90s versus 20s. All right, so this is the answers. We can practice another one on a variable width and min price. And this, I just run the code, all right? I don't show you the other, like the null hypothesis or the alternative hypothesis. And make sure that you have your data correct, okay? Here, you can run. So here again, the p-value is here, so there's no significant difference, okay? P, okay? And for the min price also no significant difference because the p-value is equal 0.39, okay? No sig detected, okay? You can do a box plot in order to see whether the twos are different or not, okay? So you can see already, no. And you can change the colors, right? Manipulate your code, okay? You can do it because we used to do it several days ago on the previous session, okay? So why lab means you need to label the y-axis. You can say minimum price of the cards. And then the x lab, it is the year period, okay? Okay. All right. And colors, okay? And say candidate, red, and blue. Okay. All right. And you can run. All right. So here it is your result. Okay. All right. So the pair sample is already done. Okay. So the next, okay, we need to do another test, which is Mann-Whitney. So the Mann-Whitney here in R, the code to conduct it is more or less the same. All right. And the variable that we are going to practice is here, MPG city, okay, compared based on the var origin, okay. So here it does not matter whether the sample size are equal or not, because it is unpaired, all right, unpaired group. The data is independent, all right. So we don't need to care about the sample, whether they are equal or not, okay. Okay, so I just want to make sure that even if it is called Mann-Whitney, in R, the code to do it is the same, Wilcox.test. The difference is the inside argument here, pair equal F, which means they are not paired. They are independent, all right? They are independent. So if we put this argument, the result of this is from the Mann-Whitney U test, okay? So just run, all right? So it is Wilcoxon rank sum. As we discussed, I explained earlier, in Mann-Whitney, it's based on rank sum. And we get the p-value here, okay? So here, p-value smaller than 0.05. If we put a star, it's 1 star. And we accept the alternative hypothesis, all right? The alternative hypothesis. Meaning that, what does it mean? Meaning that there is a significant difference, okay, between the MPG, okay, the amounts of gas the car consume when they are used in the city, okay? Which one consume less? Which one consume more, okay? So in order to see which one is more, which one is less, we do the box plot, all right? So here, we can say that the car made out of the US, if they drive in the city, those cars consume significant higher amount of gas compared to the car made in the US, as you can see, okay, in the box plot. Car made in the US have a lower distribution of data, in particular the median, all right? Okay, so here I just make a short interpretation, meaning a significant difference is detected. Okay, you can do another test, for example, with the MPG highway. We want to know whether if the two types of car, if they're using on a highway, the consumption of the gas are significant different or not. Okay, I can run now. Okay, so the p-value is here. Okay, so it means the two types of car, where they are made, whether inside the US or outside the US, they consume more or less the same amount of gasoline. Okay, we can do the box plot here. Okay, the same amount of gasoline. All right. I think that's all for our tutorial for today, and I hope you can follow what I'm showing, and you can do your own practice when you're at home. In particular, when you practice your assignment or you want to practice on your own data set. Okay, so let's have a thorough look, apply your own code, and if you have any question, just drop me a message. I'll be answering your question, your query, as long as I can. Okay, bye.